Good afternoon, everyone. My mini project is people counting. It's part of work of the ProCam, of course. This is the outline. I will mainly introduce two methods I used in this project. Okay, so firstly, the most basic question, what is people counting? Well, literally, it's to count the number of people in a certain area. During the COVID period, people counting can be an auxiliary method to help control the number of people in some places. So identify how many people are in a monitoring area is what I initially want to achieve. In this idea, this is the only question I care about. And the task can be divided into two stages, the people detection and people counting. Well, people detection belongs to the field of object detection. In this method, I use YOLO. Its full name is You Only Look Once, which indicates that its speed is very high. As you can see, this is the system of YOLO. It's a deep learning method, but only use one CNN network to predict the categories and the locations of different targets directly. The process of processing image with YOLO is simple and straightforward. This system firstly resizes the input image to 448 mapped 448. Then runs a single convolution network on the image and finally thresholds the resulting detections by the model's confidence. And these slides show the model of YOLO. YOLO made detection as a regression problem. It divides the image into an S multi-S grid, and for each grid cell predicts some bounding boxes, confidence for these boxes, and the corresponding class probabilities. The final results are based on these predictions. According to the category of the grid, we can know what the object is. And according to the maximal bounding box, we know where the object is. All in all, YOLO can detect objects of different classes, while in this project, we only want to identify people. So only this class is kept. Here is the key codes about counting. Consider that YOLO assigns a box to each detected object, and there's only one class in this case. So the number of boxes should be equal to the number of people it detects. Once we get this value, we can output it to the resulting videos. Since the video is divided into frames for detection, the people number is constantly being updated. And here's a test video. Please note that in the upper left corner of the video screen, the number of people is constantly updated. I think YOLO performs well for this scene. There are not too many people in the scene that may cause obstruction or something like that. And this test also demonstrates that for video detection, YOLO actually read a certain frame of the video and then perform detection on the picture. So this method is simple, but it has some limitations for the YOLO model because it's not specially designed to detect people. It can also detect many other objects. So the computational redundancy is very obvious. Actually, when I run the program in my PC without GPU, it really takes some time to process the video. So for real-world application, I think it's necessary to use GPU to speed it up. I also tested the model in some other videos, and I find that the shadow and the ground density can affect its performance. Apart from this, I was also thinking about the real-life scenarios to which it applies. It's apparently mainly applicable for some situations, like the camera can monitor the entire room. This lets me to think another form of people counting. Then I recalled the experience of queuing for dinner at IKEA last year. That was definitely during the pandemic, so they set a limit on the number of people in the dining area. When we arrived, there's already a long line waiting for us, and a waitress controlled the number of people at the entrance. When someone come out, new customers were allowed in. And I found that this is also a kind of people counting. So to achieve this goal, we can add a line as the prediction border to the video. It can be seen as a replace to the waitress, because through this line, we can determine that whether a person is in or out. And we only care about the people who enters. So based on this idea, I studied another method which used the mobile net and SSD to count people number. SSD is single shot detector. Like YOLO, it's also a deep learning method for object detection. Below you can see the model. The main features of it are listed here. Based on a feed-forward convolutional network, the authors of SSD add 3 auxiliary structures that can improve the prediction. And the mobile nets is a network architecture. It is designed for resource-constrained devices like our smartphones. So it's not so large like VGG or ResNet, but it may sacrifice some accuracy. The model we used here is an implementation of MobileNet SSD detection network. The combination can give a fast and efficient deep learning-based object detection. Well, now we have defined the model. Let's consider about the counting function. This counting is a little bit more complex than the former one. At first, it assigns an ID to each person because we need to track people's movement. And the program will continuously check whether people in the current screen have their ID or not. Then we need to determine people's moving directions based on the changes on the centroid. In this case, the directions are simply up and down. And the centroid is also used to judge whether a person passed the border or not. Once some of them pass the border, the program will assign the person to one of the 2 classes based on his direction. And at last, calculate and update the total number within the border. It's not difficult to find that the direction and the centroid of people are very crucial in this counting process. And here's a test video. This video is from the internet because such a top-down view is not very easy to acquire. You can see that the program performs well. Okay, as you can see, for this model, there are still some limitations. For the model, SSD was not specially trained in human data with such a view, so there's still room for improvement. And for the application, while it can be applicable in the scene I mentioned before, it still lacks some, how to say, universal applicability. For instance, if the monitoring angle of view is tilted, then the prediction border will need to be redefined also. It will not be too difficult, but it's troublesome. And I also used this video to test YOLO. you can see that YOLO cannot detect people well in some frames, like this point. Yeah, as you can see, it's not very continuous. So the data from this perspective is also a challenge for other models. And at last, I summarized the scenarios where the two methods are applicable. For the first method, I would recommend to apply it to a small place, a small place like single rooms, classrooms, so that the camera can monitor most of the place. But I think it may also be helpful in crowd density analysis if it is used in a kind of wild areas. For the second method, the entrance or the front end of a waiting queue can be also suitable application scenarios. And these are the reference the slides use. Thanks for your listening.